The last thing I want to talk about in this plane wave and lossless media video series is that there is a general relationship between the electric and magnetic field. So we made a number of assumptions previously while we were deriving the plane wave case, but let's go back to some of those assumptions and see if we can get a more general relationship. So the assumption we made was that we had the uniform plane wave, which meant that E and H were the same everywhere on some plane, in our case XY. And we made the assumption that not only was it the same everywhere, but the total electric field was in the X direction. We used Faraday's to see that it was going to be the H was going to be perpendicular. But and that we would have the direction of propagation in this case would be in the plus Z direction. But now what's to say that the E and the H must be pointed in the X and the Y direction? So we could equally just twist this, right? We could have twisted the electric field 90 degrees, and now the electric field is in the minus Y direction and H is in the plus X direction. And we still have the same relationship, that the wave is going to be traveling in the plus Z direction. So truly, we just used that simplification of E being in the X direction as a simplification to get to that solution. But we could twist it. We still have the plane wave. It's a uniform plane wave on the XY. It's still traveling in the Z direction. So it doesn't actually matter what direction the E and the H are in. We just know that these are going to be perpendicular to each other, and then that this is going to be normal. The direction of propagation is normal to that plane. And we could even have it twisted or tilted, right? Like the E field, it doesn't have to be along just the X or the Y. It could be in a little bit in the X and a little bit in the Y. And as long as the Faraday's law would continue to tell us that these are going to have a 90-degree relationship, and that the direction of propagation is going to be normal to the plane that they make, which they're both on the XY plane, so the direction of propagation is still in the plus Z direction. So we're starting to see that we can have a very general case where the electric field and the magnetic field could have both X and Y components for a plane wave, and it could be written like this. Now, furthermore, we assumed a uniform plane wave on the XY plane, but we could have selected the XZ plane with the direction of propagation in Y, right? This is equally possible. And so this leads us to this sort of generalized solution, which is that for these transverse TEM waves, right, we can relate them as the K curl E, and this E would be K curl H. And this K, right, this K is the direction of propagation. So direction of propagation. And in this case, because of the curl, this indicates, right, we have this 90-degree relationship with all three of these. And so we can also then throw out this intrinsic impedance out front. And overall, we have this generalized relationship between the electric and magnetic field for plane waves propagating in lossless media. So you could start out, you could be given an electric field and a direction of propagation, figure out what the H is. You could be given direction of propagation and a magnetic field, figure out what the electric field is. You could use the electric and magnetic field or to also determine that direction of propagation, and these will all be based on the right-hand rule as a generalization. So thank you for watching this series on plane waves in lossless media.